Hello everyone, welcome back to Analog Snippets. Switching converters often deal with high power, and high power comes with high risk. If one is not careful, part can easily go up in the flames. And for this very reason, switching converters are often armed to the teeth with various safety features. So in this video, we will discuss some of these safety features. I divide these safety features in 4 categories. The first are voltage-based protections. These protections are easiest to understand and simplest to implement. There are under voltage protection and over voltage protection in almost all switching converters. The next category is current based protection. These protections aim to limit the maximum amount of inductor current. Current limits are placed in both positive and negative directions. Third category is protection against external component short. These include protection against inductor short, and protection against shorts in any of the various off-chip capacitors. The final category is thermal protection. Switching converters can frequently get very hot, and you want to protect against any silicon meltdown. Okay, let's now look into each of them in some more details. Switching converters have a target voltage, and you would like to know if the actual voltage deviates too much from this target voltage. Under and over voltage thresholds are usually specified in terms of percentage of the Vout. A typical value can be 10%. It is not uncommon to specify an absolute voltage as well. UVP and OVP are implemented using a resistor divider to sense the Vout and a comparator with a reference. The resistor divider which is used for the main loop is often reused. These thresholds almost always have some hysteresis. As an example, the high threshold could be plus minus 10% and low threshold could be plus minus 5%. Here, high and low refers to the comparator output. A high at comparator output indicates UVP or OVP fault. And of course, you need one comparator each for UVP and OVP. Some switching converters have a third voltage-based protections to detect a large drop in output voltage. It is like UVP, but thresholds are much higher, 50% or more. This extra protection is meant to detect any catastrophic short. A switching converter can respond in different ways if an OVP or UVP indeed happens. It can shut down immediately, or it can wait for some time in the hope that these faults go away. These responses are often defined by product definition. Okay, let's now move to current-based protections. Current-based protections aim to limit maximum inductor current in both positive and negative directions. Inductor current is often sensed via sensing currents in one or both power FETs. Two most common ways to sense power FET currents are sensing current in dedicated sense resistors and sensing currents in replica FETs. For example, in boost, a sense resistor can be placed at the source of NMOS. This voltage is then processed and amplified by a sense amplifier. In current mode control loop, this same sense resistor is used for current sensing. This sense resistor is very small, ranging from few milliohms to few tens of milliohms. The main criteria for selecting this resistor is its temperature coefficient. These sense resistors are so-called zero Tico resistors, frequently having temperature coefficient as low as 100 ppm per degree Celsius or smaller. For comparison, copper Tico is 4000 ppm per C. These resistors are often made using tantalum nitride or simply TAN resistors. These resistors have complicated layout structure to ensure uniform current density and several dedicated CAD tools to analyze it. Unfortunately, not all technologies have these zero Tico resistors. So they use replica FETs. The basic idea is to have a replica transistor which is of the same type as the power FET but is much smaller. Then we create same voltage condition across this replica FET as our main power FET and then measure the current through this replica FET. As these are same type of transistor, the hope is that all the process and temperature variation will get cancelled. Of course, there is a lot of details involved, but we'll not go into those details in this video. Once we sense the power FET current, the next step is to compare it with a reference. Since we don't have a naturally accurate current reference, see video number 29, these protections often need trimming. And as it takes a finite time for the power FET to turn on, we need to wait for some time before the output is really valid. This time is known as blanking time, and depending on design, it could be few tenths of nanosecond. Okay, how about positive and negative OCPs? Let's consider boost again. So here in red we have the inductor current which is continuous, and then we have low side and high side power FET currents. For OCP you want to detect this peak current, and for negative OCP you want to detect this valley current. Now as such, this both information is available in both FET currents, but remember that FETs take a finite time to turn on. And that means if we want to sense the peak current, the low side NMOS is a better option, because high side transistor will take some time before it starts tracking the inductor peak current. On the other hand, if you want to detect the inductor valley current, you should select the high side PFET, because NFET will take some time before it starts tracking the valley current. In summary, for OCP you sense the current in NMOS, and for negative OCP you sense current in the PMOS. You can do similar analysis for other type of converters. Converters are often designed to tolerate some amount of OCP and non-OCP conditions. So make sure your metallization can survive sustained OCP and non-OCP conditions. A reasonably designed circuit can achieve plus minus 10% or better accuracy after trimming. Switching converters are surrounded by several off-chip components. Inductive switching converters have at least one inductor, often several output capacitors, input capacitors. Many have capacitors for gate driver supplies. Some may even have Schottky or other diodes, maybe off-chip snubbers as well. In short, many off-chip components. And these off-chip components can be faulty. Now, your switcher IC may be the most expensive component in the whole BOM, and you don't want your IC to get damaged if other components are faulty. So basically you need to protect the switchers against these faulty components. The fault can be either an open fault or a short fault. Open faults usually do not cause damage to the IC, and they are easily caught by normal operation. But short faults require dedicated protection circuits. So let's discuss some of them. A shorted inductor causes a very high current in your main power FET. For example, in a boost converter, a shorted inductor will cause a short between input supply and the switching node. And that means when NFET turns on, the drain is stuck to the input voltage. This effectively creates a short between the input supply and ground via a very low resistance NMOS. This high current and the high power dissipation in NMOS can kill it pretty quickly. OCP is supposed to sense the NFET current and limit it, but because of the blanking, it takes effects after certain delay. So how can we protect against the inductor short? One of the technique is to detect the voltage across this NFET when it is on. In normal operating condition, V switch take a few nanoseconds to come down. So after a few nanoseconds, if V switch is still high, that is trouble. So the key idea here is to respond fast. But at the same time, you want to allow enough time for V switch to come down. So delay of the comparator is basically dictated by these two constraints. If you detect an inductor short, you should turn off the switcher immediately. So it's very important that this circuit should not mistrigger. Let's now consider shorted output capacitor. Consider a buck startup with a shorted output capacitor. When the main switch is on, the current in inductor ramps up. Under normal circumstances, this inductor current will start charging the V out. But in this false scenario, the output remains grounded. That means in T off case, the voltage across inductor is 0. And that means inductor current doesn't ramp down, but it ramps up again in the next T on cycle. And you can guess what is happening here. Inductor current simply runs away. Now, you might argue that OCP is supposed to limit the inductor current, but because of the blanking, there is a minimum T on. And often this minimum T on is sufficient enough for this current to keep running away. So what to do? One of the options is to monitor the valley current at the end of T-off period and basically make sure that this valley current remains below a predefined value. Of course, this is not the only way to do the protection. The key point here is to understand the problem. The basic idea is that you should go through all the off-chip components and make sure that the switcher is protected against any open or short in that off-chip component. Finally, I want to spend some time on thermal protection. Part of the reason is that temperature in switching converters can quickly spiral out of the hand. And other part is my personal experience. Believe me, it doesn't look pretty if your converter starts catching fire. To say the obvious, thermal protection requires some way to sense the temperature. Now, almost all switching converters have some way of sensing temperature on die. The key point here is sensing temperature close to the source of the heat generator. And in switching converters, that source is often the power FETs. Try to place your sense element, which is often a diode or a BJT, as close to the power FETs as possible. Thermal gradients on the chip can be rather large. At the same time, heat propagation has a time constant, which could be of the order of several milliseconds. And that means if temperature sensor is not placed close to the power FETs, it may be too late before it detects alarmingly high temperatures. Now, there are tools available to do the thermal analysis of the chip, and I highly recommend using these tools for any power circuits. Another source of the heat could be discharge circuit. So pay close attention to how much power you are dissipating here. So, as we have discussed in this video, switching converters are full of these landmines. But I hope your converter is well protected and built for survival. So with these thoughts, post your comments below and thanks for watching.